Hello students, my name is Shashank Shekhar and today is the 7th lecture of the chapter Alcohols, Phenols and Ethers. So, if you look at the syllabus here, so we have covered all the physical and chemical properties of alcohol along with its nomenclature. We have seen various specific reactions and some common reactions also. Today mainly we will discuss about this acidity of phenols. Okay, we will discuss about the acidity of phenols, that what can affect this acidity of phenols. Means the substituent effects and all about those. Clear? After that, we will move to some we will see some oxidation reagents also. So some of the oxidizing reagents we will see to that. So if I talk about the previous class, so basically in that class I have covered the some of the reactions of this phenols specifically and your mechanism of the reducing agents. Regarding your oxidizing agent, we will not see the mechanism because those mechanisms are quite complicated to follow. They are kind of a concerted mechanism. So we will not look at them today. So we'll just see the reagents, oxidizing reagents, and see that which functional group transformation can it do. Clear? So let us start our today's class. So we will see first of all the dehydrogenation of alcohol. So this one thing I have left earlier. So I will cover this also. Further, we will see that which of the agents can be used to oxidize alcohol. So we'll see what is the oxidation of alcohol happened, and we will see the relative reactivity of each of this. After that, as I have told, that today's topic would be mainly about the acidity of phenol. So why is this phenol more acidic than water? We will see it, right? So we will see acidity of phenols versus alcohols. After that, this is quite an interesting topic, that is substituent effect. So if you see a phenol, it consists of a benzene ring and it has 5 hydrogens that is directly attached to a carbon. So they can be substituted or removed by a single substituent or a multi-substituent. Today we will only focus on mono-substituted one because that is only mentioned in the syllabus. So if you look here, it is very clearly written that a substituent effect of phenol, clear, of acidic nature of phenol. So mono-substituted are to be covered. Next, so let us start our today's class. So first of all, this dehydrogenation of alcohol. So if you break down this word, or you can say simplify this word, then you will see two things here. Okay, so dehydrogenation means to remove hydrogen. D means to remove what? Hydrogen. So the process of removal of hydrogen is called dehydrogenation. We have also seen a similar term. It was dehydrohalogenation, where we have removed HX. But in this class, we will see dehydrogenation of alcohol. Now, what is dehydrogenation of alcohol? So you can see here that this is alcohol, that is primary alcohol, because this carbon is connected to only one alkyl group. So if you reduce a primary alcohol in the presence of copper at 573 Kelvin. So I will not go much deeper into your mechanism, but I have put up an interesting picture here so that you can get a idea about how this reaction goes. So you do not have to worry about all of these. Okay, I'm just giving a point of view for you to think about it. Okay, so see, reactions are very interesting. So if you just imagine a reaction, you cannot imagine only the reactants and products. Okay, there are much more ingredients in that. There is your atmospheric pressure, there is your solvent, polarity, neutrons, electrons, protons. So on experimental level, these reactions are quite complicated, but since we are raising up to the standards of 12, so we look only to those reactions which can be explained using simple mechanism. So if you move to higher studies, you will see that this mechanism will become quite complicated and it will require very specific knowledge of various phenomena, electronic phenomena and steric phenomena, to get aware the mechanism of reaction. And I would say that we do not predict the mechanism directly. Okay, so if you see a reactant and a product, you cannot never predict a mechanism, although until and unless you have seen it. Yeah, the way we find the mechanism is, of course, your spectroscopy method and all, which tries to trap your very unstable transition state or your intermediate, and with the help of the study of that or isotopic effect and many more things are there. So with the help of all of those, they find the mechanism of reaction. Okay, so it is very difficult to imagine say mechanism of reaction of an unknown reaction which you have not seen until now. Clear? Now, so first is this primary alcohol. So we treat it with copper at 573 Kelvin, then it get oxidized to RCHO, that is aldehyde. So if you see the setup here that is used for say this oxidation under copper, you will see that this Cu is supported over a different type of alloy that consists of copper, zinc, Al2O4. Then this in turn is substituted on a different type of alloy. But you do not have to worry about all of this. Just think of this as a kind of hydrogen trapping machine. Okay, so this kind of act as a hydrogen trapping machine. So the basic phenomena behind this reaction is adsorption. So this CH2OH get adsorbed on this surface. Further, the two of the H2 is now further adsorbed on this surface, and the rest of this is released in the form of this. Okay, clear? So this is the kind of interaction between your oxygen mainly. So mainly oxygen is electronegative and your copper is electropositive, and the carbon. So interaction is set up, and we form an intermediate, and further the breaking of bond take place, and we got our aldehyde. So if let us see just the outcome. Let us not worry about all of this mechanism. But you see one thing here. So generally, this kind of metal catalyst, they result in a very high yield. So you can see that a 90% yield. So it is of course a very high yield, 90% yield. So if general organic synthesis, so if you perform general organic synthesis like using your general reagents, organic reagents, that would result in a very less yield as compared to this 70, 75, 80, something like that. But this metal catalyzed reaction, since they have no chance of your say lose of your reactants or something like that, because metal cannot take part in reaction, they are just catalyzing it. Clear? So their efficiency is increased, and hence it results in a very high yield. So coming back to our reaction, so if we use a primary alcohol, we will get an aldehyde. If we use a secondary alcohol, we will get a ketone. But the interesting part is this one. Okay, so this is the interesting substrate. So if we use a third butyl alcohol means an OH attached to a third butyl group. This is called third butyl. A carbon which is attached to 3 carbon, a 3-degree carbon, basically 3-degree alcohol. So for 1-degree alcohol, we got aldehyde, obvious. We got 2-degree, we get ketone. But for 3-degree, we get a alkene. Okay, we got a alkene. So to say it hydrogenation, it would be not fair. Rather than we could say this reaction as dehydration, because we are dehydrating it, kind of removing OH and H both. So we are removing H2O in this process. So this is dehydration, and also a dehydrogenation, because we are removing hydrogen at the same time. But a more appropriate word would be dehydrogenation. So the thing which is to be looked upon is this 3-degree alcohol. So if you have a 3-degree alcohol and if you dehydrogenate it in the presence of your copper at high temperature, that is 573 Kelvin, then instead of not only removing the H, it will also remove your O, which will result in an alkene. Okay, this is clear. Now, so this reaction was left in the previous class when we are studying this, say our reactivity of alcohols. I have covered this. Okay, so intentionally I have left this reaction, that is oxidation of alcohol, because I thought that I would cover reduction and oxidation at the same time. Although we have seen some of the specific oxidation reduction reaction, because they are specific, they cannot be applied everywhere, like our reaction of phenol with zinc dust. So it can be only applied to certain substituents. Next was our Na2Cr27, treatment of your phenol with this Na2Cr27 to oxidize it to benzoquinone. Okay, so those were some specific reaction. But some reagents are like that they can be used back and forth for many of the variety of substrate. So we will study all of those. Okay. So what is oxidation of alcohol? So oxidation of alcohol basically involves the formation of carbo-oxygen double bond, that is C double bond O, and the cleavage of this OH bond and CH bond. So this and this bonds are cleaved, and we get a double bond here between these two. Okay. So these two bonds are breaking, and this and another pi bond will form between carbon and oxygen. So such a cleavage formation and formation of bonds occur in oxidation reaction. So this is called as oxidation reaction. Such type of reactions are called as oxidation reaction. I'm not giving a very specific definition. I'm just saying it for this part. Now you cannot say it called. So this happens in oxidation reaction, I would say. So they are also known as dehydrogenation. So I have told you earlier. So if you are removing hydrogen, it is dehydrogenation, because it involves removal of dihydrogen from alcohol. Clear? Now, depending upon the oxidizing agent, a primary alcohol is oxidized into an aldehyde, which is turned into your carboxylic acid. So why it is written depending upon the oxidizing agent? So we have seen in the previous class, like our LiLH4, which was a strong reducing agent. So strong and weak exist for reducing agent. Similarly, it also exists for oxidizing agent. Like our LiLH4 can directly reduce our carboxylic acid to alcohol. Clear? While our weak reagents like our NaBH4 cannot reduce the your carboxylic acid. Similarly, we have some reagents which are strong and weak in case of oxidizing reagents. Okay. So if we use a weaker oxidizing reagent, then it would convert your alcohol only into aldehyde or ketone depending upon the nature of alcohol. So same logic would be applied, that if it is a 1 degree alcohol, then it would be converted into aldehyde, and if it is a 2 degree alcohol, then it would be converted into a ketone. Clear? But if we oxidize this further and the oxidizing agent is capable enough to oxidize into carboxylic acid, then it would result in a carboxylic acid. Or we can convert this directly into this, although the intermediate is formed, this intermediate would be formed, but we cannot stop reaction in the middle. We cannot use a very strong oxidizing agent like our, say, this KMnO4. Okay, this KMnO4, or you can think of a more strong oxidizing agent like your, say, PCC. Okay, so you cannot use all of those to convert into aldehyde, only into aldehyde. It will convert into carboxylic acid. For the case of ketone, you cannot do it so, because it requires the cleavage of CC bond. We will look at this all. So what I'm saying here is that if you have a ketone, suppose you have a ketone, you have alcohol here that is 2 degree in nature. Okay, it is attached to 2 carbons and 1 hydrogen. Now if you oxidize it further, it will get converted into ketone. Clear? But if you want to oxidize this much further, then you have to form a OH bond here. For this, you have to break this bond. Okay, so this would require very strong reducing agent. Clear? Obviously, we will not see them very often, but there are reagents which can convert directly ketone into carboxylic acid, but they are very strong in nature. Clear? Now, let us move to some of the reagents that can be used to convert our functional groups into our required functional groups. So starting from primary alcohol. So if you are seeing a primary alcohol, and if you use reagents like KMnO4, K2Cr2O7 or CrO3, then aldehyde, this 1 degree is converted into aldehyde and then into carboxylic acid. So what is the note here? That initially we form aldehyde, which is further oxidized into carboxylic acid. So we cannot stop the reaction in the middle. Considering about your this reaction, that is 2 degree alcohol. If you consider a 2 degree alcohol, so as I have told that to convert into carboxylic acid, it would require very strong reducing agent. We will not see all of those. So if you take a secondary alcohol, then it will be converted into ketone only. at KMnO4 with the help of KMnO4, K2Cr2O7 or CrO3. But if you have a 3-degree alcohol, that could not be converted into anything. Okay, we do not have a conversion to any further oxidized state. Yeah, it can be converted into alkene if you use that copper thing. That is also oxidization because you are removing hydrogen. But if you use KMnO4 at elevated temperature, then it can result in a carboxylic acid. Okay, so it would require CC bond cleavage. Okay, so this reducing engine can be used. So it is very rare to see this kind of oxidation. Okay, other than copper one, we can see the copper one because that is a quite common one, because basically we are converting our alcohol into an alkene. So it is also oxidation, I have told you earlier. Now let us move to our today's main topic, that is okay. So before that, yeah, so we have a reaction here. So as I have told you earlier, so this is called PCC. So PCC is basically pyridinium chlorochromate. Pyridinium chlorochromate. This is pyridine. So it has a structure. It has a chromate. So chromate looks like this. Okay, I'm not very sure about the structure. Yeah. So pyridinium chlorochromate, it is a Cl minus also. Sorry. So I'm not very sure about the structure. We will, if I look into it, I will surely put up the slide in the next class. But for now, assume that PCC is something that can oxidize this thing into aldehyde only, and it will be not further converted into ketone. As contrary to these things that will convert your primary alcohol directly into carboxylic acid. Clear? Okay, now we will move to these things, that is acidity of alcohol, phenol. What? Acidity of phenol. So what happens here? So basically these phenols are more acidic than alcohol. The reason behind it very clear, that your phenoxide ion that would be formed. So we'll see in the next slide. The phenoxide that is formed in case of alcohol also, that is called alkoxide. So both of these have a negative charge on oxygen. So after we remove our proton, we get a negative charge on oxygen for both for phenol to get phenoxide and alcohol to get alkoxide. But the difference between two of these is that the negative charge on oxygen in case of phenol can be delocalized into your benzene ring. We will see the delocalization in the next part. Okay. Due to this reason, this phenol is more acidic than alcohol. How can we find out the acidity? Just treat your metal with this phenol with any metal or sodium hydroxide. Then you will get the hydrogen gas or CO2 depending upon what you are using. And this reaction are given only by your acidic component. So we'll come to know that these are acidic in nature. So the hydroxyl group in phenol is directly attached to sp2 hybridized carbon of benzene ring, which can act as an electron withdrawing group. So for a substance to be acidic, there should be a withdrawing group. So if an electron withdrawing group is present on your substrate, then it will make your substrate more acidic. And you know it very well that if it is this kind of forming this kind of structure, and its lone pair are delocalized over the ring. Now due to this reason, the oxygen is getting positively charged for some time, of course in some resonance structure only, but it it has a development of partial positive charge due to resonance also. Due to this reason, we have more facilitated the removal of your H plus. Okay, clear? Because this H plus has to leave, a proton has to be removed. So if the negative charge is attracted towards one, then we can remove your proton. And how can it be seen? So we have seen this resonance in case of your electrophilic aromatic substitution also, where we have told that okay, since this oxygen is donating its electron to the ring, so it is activating the ring. So if it is activating the ring, it must be getting deactivated. Okay. Now one more thing to notice here is that we have a negative charge on these things here. Okay, so suppose further this negative charge is stabilized. So if that case happens, if we have an electron donating group, okay, then if this happens, then it would not be appropriate to do the resonance. So we'll see to that. Okay, we'll see to that. Now next, let us first compare the acidity of phenol and alcohol. So the very obvious reason for your more this acidity of phenol is the sp2 hybridized carbon. So this is the most obvious reason. Of course, we have this resonance factor, but this is the most obvious your factor, because this carbon is sp2 hybridized. sp2 hybridized means it has greater s character as compared to this R, which has carbon which is sp3 hybridized. So this is the very obvious reason. Now since it is sp2 hybridized, it has greater s character as compared to sp3. So sp3 has 25% s character and sp2 has 33.333 s character. Now since there is more s character, and s character means the electronegativity of the carbon is more. Okay, so this carbon that is present in phenol is more electronegative than the carbon that is present in alcohol. So it will attract your now this will be more electron withdrawing, this will be more electron withdrawing. So it will withdraw your electron from oxygen and will develop a partial positive charge on oxygen, which will be more, not partial positive charge, sorry. So of course this charge is developed in oxygen, delta negative and delta positive. So if we reduce this charge in any way, then this H plus removal is facilitated. So if we use a more, say, electronegative element in this position adjacent to this oxygen, then it will reduce the negative charge on this oxygen, and hence the removal of hydrogen will be facilitated. So since we have a sp2 carbon which is more electronegative due to the greater percentage of s character, therefore these phenols are more acidic than your phenol, so alcohol. So this is the most obvious reason. So it is written that due to the higher electronegativity of your sp2 hybridized carbon of the phenol to which OH is attached, electron density decreases on oxygen. Now this increases the polarity of OH bond. Okay, this increases the polarity of OH bond and result in a increase in ionization of phenol. So in turn it also increases the polarity of your OH bond, and OH bond polarity increases means the charge on oxygen increases, and the charge negative charge on oxygen increases, and the positive charge on hydrogen decreases, and that will of course facilitate your removal of proton. As compared to alkoxide ion, the negative charge is delocalized on oxygen, while in phenoxide ion the charge is delocalized. So it is saying that that in case of alkoxide, so I have told you earlier this thing, that if in phenol, if we remove the hydrogen, we will get this type of thing, that is phenoxide, and you can see that this negative charge has been delocalized throughout the ring on ortho and para position. But if you take the case of your alkoxide, suppose we have this thing. Now this negative charge is localized. Localized means, what is meaning of delocalized and localized? So delocalized means that is something which is mobile, which is always moving. It is called delocalized. And localized means it is fixed at one place. So in case of your, say, alkoxide ion, since the negative charge is fixed on one place, therefore it will be not that much stable. So think it in that way, that if you are suppose you have a weight on yourself. Okay, if you have a weight on yourself, and now I am putting more and more weight on you, then you will of course feel uncomfortable. Now just try to apply that similar analogy of uncomfortability to your higher energy. So since it has a negative charge and it is only localized on oxygen and it has been not distributed throughout the carbon ring, so that would result in kind of instability or increase in energy of the system. Therefore this system become unstable. Now what is the effect of this? Why are we looking at the stability of the phenoxide ion or alkoxide ion? So the answer lies behind your Bronsted-Lowry acid concept. So if you see that overall reaction, I'm just taking the one of the part, I'm not taking the whole reaction here. Similarly, you have a phenyl. So first of all, what is Bronsted-Lowry concept? So we have the concept of conjugate acid and base. So if an acid is weak, its conjugate base will be strong, and vice versa. Both are correct. Now, suppose this is stable. If this is stable, then the rate of acceptance of H plus will be less. That is the basicity would be less of this one. Clear? So since its basicity is less, that is, it is a weak base. So its conjugate acid will be stronger. Okay. So since it is a weak acid, therefore the conjugate acid will be stronger. Whereas in this case, since it is stable, it will not accept your hydrogen very efficiently as compared to this one, which is unstable. Therefore, it will not move in this direction, or you can say it is less basic in nature. Therefore, it is a stronger conjugate acid. So, if you want to compare these two, you can just look at their conjugate pair to get a good comparison. So, although there is a charge delocalization of phenol, its resonance structure has charge separation, due to which the phenol molecule is less stable than the phenoxide ion. So, it is written that although we have a delocalization of charge, so basically what we are doing, we are comparing this phenol with your phenoxide. So, although we have a delocalization of charge in case of phenoxide, but we have a separation of charge. So, we have a charge appearance, and neutral species are stable than charge species. So phenol is more stable than your phenoxide ion. Clear? So this is the comparison of phenols and alcohols. Now let us move to a more interesting topic, I would say, that is substituent effect on acidity. Okay, substituent effect on acidity. So let us first understand what is the substituent. So in substituent phenol, the basically what is substituted phenol? So what we are doing, we are taking a phenol. So the phenol has 6 hydrogens, out of which one is attached to your oxygen and the other 5 are attached to the carbon. Okay, so let me draw it for you. So this is the structure of phenol. So we have hydrogens here all over this carbon to complete the valency. Now, what is substituted? Suppose we have a group X which has a valency of 1, which has a valency of basically +1. Okay. Now, what we are doing? We are taking this thing, this hydrogen, and we are substituting it with this X. Okay. It does not mean negative sign. It means that it can form one bond. It is a monoatomic thing, monoatomic species. So suppose we substituted this hydrogen. Okay. So I'm not representing all of the remaining one. Let me represent it. So that would make a more clear scene. Okay. Now we have a X here. So we have substituted your H with X. So this is called your substituted phenol. Now the nature of X, first of all, the nature of X and the position of X, where it is present. So we can substitute this hydrogen also. So we have substituted this one, we can substitute this one also, this one also, this one also. So depending upon the position of your hydrogen, we will see that how this acidity is affected by the substituted group, and also upon the nature of the substituted group. Both will decide your acidity. Now, in substituted phenol, the presence of, as I have told you earlier, so if there is something which is attracting your negative charge towards it and removing the negative charge from your oxygen, then it would more polarize the bond. Therefore, it will result in a greater acidic character. Okay, it would result in a greater acidic character. So in substituted phenol, the presence of electron withdrawing group such as nitro group. Okay, so this nitro group is the electron withdrawing group. So I have told you earlier that if we have electron withdrawing group, then it will deactivate the ring. So if you have an electron withdrawing group, then this can enhance the acidic nature of phenol because it is making the OH bond much polar. So this effect is more pronounced. So if here comes the technicality. So if your electron withdrawing group is present in ortho and para position, okay, so if something is electron withdrawing, and which kind of electron withdrawing, which is withdrawing your electron to resonance. I'm not talking about the chlorine and all. So they also deactivate the room or with the group or the benzene, or they also are kind of electron withdrawing, but I'm not talking about them. So the one which deactivate the ring by, say, resonance effect, for that type of substituent, so if there are at ortho and para position, then that effect will be more enhanced. Okay, so they will kind of increase the acidity more. Why it is so? Because as I've told you earlier, because due to the effective delocalization of negative charge in phenoxide ion. So if you have a negative charge both on ortho and para, so due to the presence of your electron withdrawing group, that negative charge can be stabilized. Therefore, the O plus species or the phenoxide ion, if you look at the resonance structure, you will see O plus species, oxonium ion species. So that will be kind of more stable. Clear? Whereas on the other case, if you have electron withdrawing group such as an alkyl group, so since an alkyl group donates electron in two ways, first of all by hyperconjugation, and second by your plus I effect. So if we have an electron donating group, then that would decrease the acidity of your phenol. Okay, that would decrease the acidity of phenol. So for that, cresol is an example. So we'll look at each of these one by one. What is ortho cresol, para cresol? We'll see why the acidity and base acidity is decreased or increased. But for now, if you want to put all of this in a nutshell, I would say, so if you have electron withdrawing group in a phenol, then that would increase the acidity, and if we have an electron releasing group, then we can say that it decreases the acidity. Now if it is present in ortho and para position, then electron withdrawing group will make the acidity much higher as compared to meta position. Similarly, if you have a electron withdrawing group on meta position, okay, if you have an electron releasing group on ortho and para position, then it would make this phenol even more less acidic. So here's a table. So we will quantify this table one by one. So if you look here, then you can see that we have pK values. Let me make a physical chemistry point here. So this is a thing from ionic equilibrium. So if something has a greater pKa, that means it will have a lower Ka. Lower Ka means lower H plus concentration, means less acidic. Why are these relations so? Because it's equal to not good. Yeah. So what is first of all pK? It is minus log K. Now here you can see that if we increase the value of K, log K will increase, but overall value will decrease, that is of pK. Therefore, if we increase pK, K will go down. Now K is what? Acid dissociation constant, which involves the concentration of H plus divided by the species. So if K is decreasing, your H plus will also decrease because K is directly proportional to H plus concentration. So this H plus will decrease. Therefore, the release of H plus is decreasing, so it will become less acidic, because that is the definition of your acidity by Arrhenius, that says that if a substance is able to donate its H plus, then it is acidic. So if it is donating less H plus, then it is less acidic. Clear? So if something has a greater pK, means that is less acidic. So if you look here, so first of all, let us compare all of these three. So in these three, we can say that this one has the highest pK. So M1 has the least acidic character. Then we have this one, that is ortho, and then we have your para. Okay. Whereas, so this is for your nitro one. Now if you look at cresol, so basically cresol looks like this. So if it is phenol, or this is orthocresol, sorry. So if it is orthocresol, means we have CH3 group on the ortho position. Clear? Now, what is this thing that is orthocresol? So out of these three, you can see that ortho and para have almost same pK. So we have not kept the value after this decimal. So we have only moved to first figure. So according to this first figure, it is obvious that this ortho 1 and para 1 are almost same acidic. But this meta 1 is more acidic as compared to both of these. Okay. But you will see this ortho and para will also be defined. So if you just write the further value of this or the further significant figure of this ortho and para, you will see that one of these will become more acidic. Coming to our ethanol and phenol. So if you now compare each of these substrates, so one substrate is this, one substrate is this, one is this, and one is this. So the alcohol one is the least acidic as it has the highest pK values for the obvious reasons which I have mentioned just now. Then we have the least acidic as your, say, cresol. So this is basically due to the electron donating nature of CH3, and how it do so we will see it. Then we have the phenol. So since it is kind of a neutral between this nitro and cresol because it has no substituent, so it is in the middle. Then we have the nitrophenol, which has an electron withdrawing group, therefore its acidity is higher as compared to all of this because it has an electron withdrawing group. But what is the reason behind this ortho, meta and para trend? We will see it right now. Okay. So first we will see for nitro group. Okay. First we will see for nitro group. So what is the reason behind it? If you look first time, you will notice that since NO2 is present at ortho and para position, if it is present at ortho and para position, then both of these would be higher, because I have told you earlier that if it is present at ortho and para, it will stabilize the negative charge of the phenoxide ion much easier. But you can see that this nitro position is present as para, it should have a higher pK value, sorry, K value. Why? Because this ortho position is more more nearer to your phenol group, so it would apply more inductive effect, plus your resonance effect is not dependent upon distance that much. Therefore you will see that okay, this would have been a greater acid, but it is not so. So the reason behind it is this thing, your intramolecular hydrogen bonding. So I mentioned it earlier also when we were nitrating your phenol and we were trying to separate this mixture. So this was the reason for more volatile nature of this phenol. Okay, nitrophenol, orthonitrophenol, and this is also the cause for less acidic nature of your orthonitrophenol because of the hydrogen bonding. Now since it is bonded in two ways, so there are two type interaction. First is clearly a bond between O and H. Second is the interaction between your lone pair of oxygen and hydrogen. Now this would affect the acidity of this orthonitrophenol because this release of H plus is difficult as compared to your ortho and para one, which has a free H. Okay. Now you got the idea why we have your ortho first, less acidic than para. Then at last your meta, because since it is present at meta position, and you know that this phenoxide ion negative charge does not comes on your meta position, so it is not that much stabilized, but still it has NO2, so it is kind of deactivating the rings, hence making the ring more electron deficient and kind of stabilizing the extra negative charge on oxygen. Clear? Now I have not put up the slide for cresol. Why is this nature of cresol seen? So I will show it to you. So if you look at three structures of cresol, it looks like this: OH, CH3. Sorry, this is orthocresol, this is paracresol, and this one is metacresol, and this one is paracresol. Now in what ways this electron donating group are donating the electrons to this phenol. So first, the obvious way is plus I effect. Okay, this is an obvious for all of these three. All of this will have plus I effect, but in contrast to this meta, these two have another effect, that is hyperconjugation effect. And hyperconjugation effect, so if you try to draw the structure, you will see that it is increasing the say charge, that is your negative charge on these position. Although this hyperconjugation is much more not pronounced as compared to your resonance, but it has an effect. So since this I effect is distance dependent, and it is obvious from that it should have a greater plus I effect and hence less acidic. And plus we have this, say, your hyperconjugation, and hyperconjugation is for both this and this. This is not for your this thing, that is a meta. So if you just try to hyperconjugate this thing, you will see that this increase the negative charge here, here and here, similar to your resonance, but this negative charge is not that much pronounced. Okay, so for that reason we have a greater smaller acidic nature than of ortho. Ortho is the most acidic one, the least acidic one. Then we have our para, and then we have a meta. Okay, so this is the order for cresol. Okay, but if you see in your say table of your NCERT, you will find that two of them are same shown, that is ortho and para one. But if you just observe it more accurately, you will find that ortho is less acidic than para. Clear? So today we have covered this substituent effect of your phenol. Okay, so this is and we have seen the oxidation reaction. So with this our alcohols and phenols are over. Now we have left with the ether. So basically ether are something which is attached to oxygen. Two alkyl groups are attached both sides on oxygen, and they can be symmetric and unsymmetric depending upon the nature of the alkyl group that is present on both sides. Clear? So with this I would end my lecture. Thank you.